In this video, I'll talk through the National 5 Chemistry Unit 2 topic of homologous series. By the end of this video, you should be able to name and draw structures for different hydrocarbons, be able to explain the trends in melting points and boiling points in terms of intermolecular forces, describe how to test for saturated and unsaturated compounds, and also be able to complete addition reaction equations. Starting off with the definition of hydrocarbons. Hydrocarbon is a compound containing carbon and hydrogen only. It's important when you're asked to give the definition, the only part is really important. If you look at these two chemicals, both of these have got carbon and hydrogen, but it's only the one on the left that would be a hydrocarbon because it's only carbon and hydrogen. Next definition is homologous series. A homologous series is a family of compounds with the same general formula and similar chemical properties. Examples of these would be alkanes, alkenes, and cycloalkanes. Watch out for if they're asking you to tell them an example or to give the definition. When it comes to naming hydrocarbons, we need to know the beginnings and how many carbons they refer to. We have meth, eth, prop, but, pent, hex, hept, and oct. You can be asked to go up to 8 carbons in the longest chain. There are names of some of the hydrocarbons on page 9 of the data booklet. They are in order from 1 up to 8. The first homologous series we look at are the alkanes. Alkanes have carbon to carbon single bonds. Their names will end in ane and ane. When it comes to drawing formula, you can be asked to do 3 different types of formula. A full structural formula will show you all the bonds between the atoms. When it comes to a shortened one, we've shrunk it down a little bit, and we tend to group the atoms joined to each carbon in the chain. And a molecular formula just shows you how many of each atom there are in a molecule. Using the alkanes as an example, we have methane, ethane, propane, and butane. You can see there the full one shows all the lines that connect the carbons and the hydrogens. We then take each carbon bit by bit. So if we break them up in here, so in taking propane an example, we have CH3, then a CH2, and then we have a CH3 as well. And for molecular, we've just counted up how many C's are there, how many H's are there, and write them out like that. We can be asked about general formula, which is a connection between the number of carbons and the hydrogens. The pattern, as you can see, is every time we add on a carbon, we have 2 more H's getting added. Problem comes, what happens if you're asked about 50, 60, 70? It's not a good use of time to go through and keep working up C9, C10. It will take far too long. Now, the connection between them is that the number of hydrogens is double plus 2, however many carbons there were. And to write that as a general formula is Cn H2n plus 2, where n stands for number. So here you could be asked for the molecular formula for an alkane with 10 carbons. It's going to be C10. It's going to be double and add 2. Double 10 gives you 20, plus the 2 gives you H22. So C10, H22. Next one we're asked to do 14. Same again, double it, 28. Add on 2 gives you 30 hydrogens for that one. In this next one we're asked about 30 carbons. Double it, gives you 60. Plus 2 gives you 62 hydrogens for that one. And in this, the last example, you might spot that here we are told that there's 82 hydrogens. So we have to work backwards to figure out how many carbons there'd have to be. What we would want to do is take away 2 first of all, bring this down to 80, and then half it to give you 40. Sometimes people try and half it first and then take away 2, which would give you the wrong answer. Easy way to check, just put the 40 back in, double it, 80, add on 2, gives you 82. So you can use it forwards and backwards to make sure you're doing the correct thing. Next, we move on to our second homologous series, the alkenes. Alkenes contain at least 1 carbon to carbon double bond. It's important to say that because other chemicals will have a carbon to, say, oxygen double bond, which is a little bit different. Here are the diagrams for each of the first 4 alkenes. One thing you'll notice is that we start off with ethene, because to have a carbon to carbon double bond, you have to have at least 2 carbons. So there's no such chemical as methene. That's not possible. When it comes to our structural formulas, there's 2 kind of ways we can do it. Now, this way at right angles is easier to draw in your jotter. It looks neater and tidier. They would exist more angled here because that keeps the atoms as far apart as possible. So you might see a mixture of these shapes as you move through the course. When it comes to the shortened ones, we're again just splitting at every carbon and we're writing down how many H's are attached to each of them. And at the very end for molecular, we are grabbing all the carbons together and then all the hydrogens together as well. When you get asked about the general formula for this one, we can hopefully see that it's just double. So the number of hydrogens is double the number of carbons. As a general formula, that's CnH2n. As some examples, if you have 9 carbons, you're going to have 18 hydrogens in your chemical. For 17 carbons, you'd have 34. This time, we've got 30 hydrogens, so it has to be 15 carbons. And then for 44 carbons, it'd be 88 hydrogens. Like the third homologous series we're going to deal with are the cycloalkanes. They contain carbons connected in a ring. What you can see here is that we have our different shapes of the carbon rings. We have our triangle, our square, and our pentagon. When it comes to the shortened structure formulas, we want to make sure as best we can that the connections are coming out of the carbon, because carbon can make 4 bonds, hydrogen can only make 1. It's a bit awkward here with the software I'm using. My one at the bottom I'm not entirely happy with, but you should hopefully be able to get the idea. Similarly with the molecular formula, we're just grabbing all of the carbons and then all of the hydrogens together to get your molecular formulas. Comes to the general formula, it's again just doubling the number of carbons to get your number of hydrogens. That is a general formula of CnH2n. If we're dealing with 7 carbons, double would be 14. 19 would give you 38. 12 would give you 24. And if you have 44 hydrogens, you need 22 carbons. Next part, we'll talk about our intermolecular forces. These are the attractions or forces that exist between molecules. If you look at the alkanes, alkenes, or cycloalkanes, there's a gradual change in melting points and boiling points as they get bigger and bigger and bigger. We can see that on page number 9, where something like hexane has a higher melting point than ethane. Be very careful with the negative numbers. Negative 183 is a lower number than, say, hexane with minus 95. So we're getting closer to 0, so we've got a bigger number. The typical question that you'll get asked is to explain why something has the higher melting point or boiling point. As the size of the molecule increases, there are stronger intermolecular forces. So something like pentane will have stronger intermolecular forces than something like methane, 5 carbons versus 1 carbon, or something like that. So higher melting point and boiling point indicates stronger intermolecular forces in your alkanes, alkenes, or cycloalkanes. Moving on to another definition, we have isomers. They are molecules which have the same molecular formula but different structural formulas. If we take something like butane, butane has 4 carbons, and because it's an alkane, it will have single bonds between the carbons. First one is just straight up butane, 4 carbons in a row connected together. The second one is called 2-methyl propane. We'll get 3 carbons in the longest chain, 1 sticking out as a branch. Watch out for ones like the ones in red, but at first glance it looks different to the top 2. However, if we are describing it, we have got 4 carbons connected together in a chain. We have the same in the first one. These 2 are identical molecules. They're the same chemical. They're not isomers of each other. That's something that teachers and exam writers will do to try and throw us off a little bit. So watch out for the longest chain could turn around the corner. Something that you can do to help identify if you have a chain that's turning around the corner or if you have branches is to think about highlighting or actually highlight the carbons. You're not allowed to double back on yourself. So in the one at the bottom, I can go and highlight all 4 of the carbons without doubling back on myself. Whereas in this one, the most I can do is 3 going from left to right. I can't include the one sticking out at the top unless I double back on myself. Even if I wanted to go up the way and include that one, the most I can get is 3 in a row with 1 branch sticking out. 5 rules that if you follow, you'll get to the correct naming. The first thing to look for is the longest chain of carbons, which gives us the main part of the name. That is meth, eth, prop, but, etc. If you have any branches, so the sticking out carbon or carbons, that needs to be given a number, a value to tell you where it's sticking out of. When you're numbering a chain, you want to start from the end nearest to the branch. We want the lowest value for our branches. Every branch has to have its own number. That's when you have things like di and tri methyl and things like that we'll come on to. If you have a carbon-to-carbon double bond, it takes priority for the numbering. So you have to make that have the lowest value first before you start doing the branches. It's similar to when you have an hydroxyl group for alcohols, which is in a future topic. We'll now go through some examples which put those rules into practice. So first thing was the longest chain of carbons. Looking at this compound, we have got 4 carbons in the longest chain. 4 is given the beginning bute. It has carbon-to-carbon single bonds, therefore it's butane. Just as straightforward as that. When we have branches, we need to give the branch number. We have got 3 carbons in a row, meth, eth, prop. It's single bonds between the carbons in the chain. That's going to be propene. We have a branch sticking out of carbon number 2. It's a 1 carbon branch, which is why it gets the name methyl group. If it was a 2 carbon branch, it would have been ethyl, and so on. So we have, off of number 2, we have a methyl group. So putting it together, 2-methyl propane. When it comes to naming ones with branches, don't try and do it all at one time. Get your longest chain first and then deal with your branches. We are now going to deal with numbering from the end nearest to the branch. If you just went from left to right, we might say that you've got a methyl group off of the 3rd. If you go from right to left, we would say we have a methyl group coming off of the 2nd. We want the smallest value for the branch. That means that this is going to be 2-methyl butane. We'll have 4 carbons in our chain with a methyl group sticking out of the 2nd carbon of the chain. In this one, the longest chain we can make is 3. Now you could make 3 going straight up and down the middle. Just looks nicer going across from left to right. You still get the same name. We have 3 carbons, so it's going to be prop. It's single bonds between the carbons, so propane. At this time, we've got 2 branches, both coming off of the 2nd carbon. That is put together by saying it's 2-2. Every branch needs its own number. It's dimethyl because there are 2 methyl groups. We have 3 carbons in a row with 2 methyl groups coming off of the 2nd carbon. When it comes to your branches, their names are based off of the alkane that they've came from. So methyl, ethyl, propyl, if it was a large enough chemical we could get to there. Most likely it's going to be methyl with maybe a little ethyl group thrown in. This example is probably up at the upper end of difficulty that we could be faced with at National 5. We're going to just do our usual steps. Number 1, what's the longest chain? Well, there are 7 carbons in the chain. 7 is given hept. It's single bonds between the carbons, so it's going to be heptane. Next thing we're going to deal with are 2 branches. We have a 2 carbon branch off of number 4. That is an ethyl group coming off of the 4th carbon for ethyl. We also have a methyl group off of the 2nd carbon, so 2-methyl. It should be in alphabetical order by the name of the branch. For ethyl, 2-methyl heptane would be the full name for that one. Next, we're going to add in our carbon-to-carbon double bonds for an alkene. And we've got 2 isomers of butene here. What we're looking for is where is the carbon-to-carbon double bond. In the first example, it's between the 1st and the 2nd. We take the lowest value, that's going to be your but1ene. And the second one is but2ene, because we have the carbon-to-carbon double bond shuffled over into position 2 for that one. When you have got a carbon-to-carbon double bond, it takes priority for numbering. So we're going to ignore the branch for now. We're going to look at, well, if we want the lowest number for the carbon-to-carbon double bond, it's going to be 1ene. That is set in stone now. That is fixed. That means our methyl group, the branch, is coming off of the 4th carbon. If you were to go from right to left, you might be wanting to call the methyl group number 2. But if that was number 2, then your pentene would be 4 rather than 2. And the next one, what's the longest chain? We have 6 double bond between the second and third, so hex 2-ene. We have this time got 2 methyl groups coming off of the 5th carbon. That's going to be 5,5 dimethyl hex 2-ene. So hex because there's 6 in a row, 2-ene because the double bond is in position 2. 5,5 tells you there's 2 branches coming off of the 5th carbon. Dimethyl means they're both single carbon branches that come off of it. We can also have isomers of cycloalkanes as well. In this one, we have a 6 carbon ring called cyclohexane. We have a methyl group coming off of the ring. With one like this, we don't need a number because wherever that carbon branch is would be position 1. You could call it 1-methyl cyclohexane, but there's no point in doing that. With one like this, where we have 5 carbons in a ring, so cyclopentane, we have got 2 branches coming off of the ring. If we pick one of the branches and number it as position 1, then the other carbon branch is coming off of position 3. 1,3-dimethyl cyclopentane would be your answer for that one. Next part we need to know about are saturated and unsaturated compounds. Alkanes and cycloalkanes are saturated. They have carbon-to-carbon single bonds. An alkene would be unsaturated as they have at least 1 carbon-to-carbon double bond. Now, to test if something has carbon-to-carbon double bonds, we can use bromine water or bromine solution. We'll mix the bromine with our sample. Unsaturated compounds will decolorize bromine water quickly. This reaction that unsaturated compounds do with bromine is called an addition reaction. The carbon-to-carbon double bond breaks apart and we add on atoms onto the new bonds that are formed. Where this can be useful is if you have samples of hydrocarbons that you are not sure if they have carbon-to-carbon double bonds, we can test them all with bromine. So in this setup, we've had our 4 results of A and C do not change the colour, whereas B and D did decolorize bromine solution. That means that the no colour change have no carbon-to-carbon double bond, whereas B and D do have at least 1 carbon-to-carbon double bond. When it comes to saturated or unsaturated, well, if there's no double bond, that means it's single bonds. So A and C are saturated, whereas B and D are unsaturated compounds. We've also been given our chemical formulas, and we can be asked to piece all those bits of the puzzle together to come up with a possible structure for the chemical. So for A, we have no carbon-to-carbon double bonds, and we need C6H14. That is double plus 2. That means it's going to be an alkane. The most straightforward one would be hexane, just 6 carbons joined together. You could have 5 carbons with 1 sticking out. So we could have 2-methyl pentane would be another option. Depending on the question, you might have more than one possible answer. This one, we have got a carbon-to-carbon double bond. We are C6H12. That's going to give you an alkene. In this case, I've went for hex 1-ene. You could have went for hex 2-ene. You could have had some branches as well, just depending on the question. Here, well, we want to have single bonds between the carbons, but we also want to have C6H12. The CnH2n is true for alkenes. This cannot be that. Also, cycloalkanes. So cyclohexane would be a good option for that. We could also have methyl cyclopentane, which would be that chemical on the right hand side. And the last one, we have got at least 1 carbon-to-carbon double bond. This one's a bit different because it's CnH2n minus 2. So we've lost another 2 hydrogens. How could we do that? Well, we could have something that has 2 carbon-to-carbon double bonds. Or we could have a ring structure which also has a carbon-to-carbon double bond. As long as your structure satisfies the C6H10 and has at least 1 carbon-to-carbon double bond, that would be correct for this information that we are given. Alkenes can undergo addition reactions with various different chemicals. We could use hydrogen. That's described as being hydrogenation. We could have halogenation, which is adding a group 7 element, one of the halogens, or hydration is the addition of water. The first thing is look at the double bond between carbons 1 and carbon 2. We're going to open that up, and that now gives space for the 2 bromines to be added together. It's 1,2-dibromo because we have a bromine off of the first and a bromine off of the second, and then propane now because it's got single bonds between the carbons. So it's now an alkane for that one. So that's an example of an addition reaction using a halogen such as bromine. In this one, we're going to do hydrogenation, where we're adding hydrogen. We want to break the carbon-to-carbon double bond and slot in the 2 hydrogens. That takes us from an alkene to an alkane. In a hydration reaction, we are adding water, and we are going to make an alcohol. So on the 2 positions, we're going to add an OH to one of them and a H to the other one. Now with this setup, we could actually have 2 different versions. So in the first one, I've added to the left-hand carbon of the carbon-to-carbon double bond, I've put the OH and I've put the H on the right. Whereas in the second one, I've done it the other way around. So you'll see there's a H on position 2 and an OH on position 3. So these are 2 possible products from this type of reaction. I'm still breaking the carbon-to-carbon double bond, and I'm adding in 2 things. Now we're going to look at exam style questions. In this first one, job 1, find the longest chain of carbons. Now you might have been lured in by the 3 at the bottom. Well, in fact, we can have 4 carbons in the longest chain. That puts it down to either C or D. What else do we have? We have a branch coming off. When it comes to the numbering, we want to number from the bottom right chemical. That would be position 1 and position 2. That makes it 2-methyl-butane for the answer of C. So they've tried to catch us out with putting it around a corner, but it's still 4 as the longest chain. In this one, we're asked about heptane. Hept is 7 carbons. Alkanes are CnH2n plus 2. That means we're looking for C7H16. So one of the things we can do quite quickly is to count up the numbers of carbons and hydrogens that we've got. So in this one, only B has the same number of carbons and hydrogens, and an isomer has to have the same molecular formula, but a different structural formula. So in heptane, we'd have all 7 connected in a chain, whereas for B, you see there's 6 carbons in the longest chain with 1 carbon as a branch. So only B is the isomer of that chemical. Something that they can do, so say we had 2 options with C7H16, they could make it look like this. But the one on the right, again, if you don't catch that is 7 in a row, just because it's around a corner doesn't mean it's a branch. It's exactly the same chemical. So they are not isomers of each other here, they are the same chemical. In this one, we're asked about homologous series we're not directly taught about at National 5, and we're asked for the general formula. First thing to do is count up the C's and H's for each of them. That gives us C4H6, C5H8, and C6H10. What we then want to do is figure out what connection can we have to figure out the number of hydrogens from the number of carbons. They all tend to start with CnH2n. So if you doubled up 4, that gives you 8. You need to knock off 2 to get down to 6. Check that would work for the middle one. Double 5 gives you 10, take away 2 gives you 8. Good. Double 6 gives you 12, take away 2 gives you 10. That means that A would have to be our correct answer for this one. It has to fit for all of the chemicals. It cannot just fit for one of them for that. So A would be correct there. In this one, we're asked about a compound that fits CnH2n and will decolorize bromine solution. That's 2 parts to this one. For the general formula, that's the alkenes or the cycloalkanes. And unsaturated compounds will decolorize bromine solution. That means they have to have at least 1 carbon-to-carbon double bond. And only D ticks both of those boxes. A, cyclopentane would have CnH2n, but it doesn't have a carbon-to-carbon double bond. B wouldn't fit CnH2n, but would decolorize bromine solution. Pentane wouldn't do either of them. Pentane does both of them. If you don't remember what the general formulas are, you could still have sketched them out and drawn them out, and you would see how many hydrogens they've got. in them would be another approach. Next one, we're asked about the test to see if something is unsaturated. We'll have to remember that unsaturated means it has at least one carbon-to-carbon double bond, and an alkene would decolorize bromine solution quickly. Next one, we're looking at different reactions that an alkene can undergo. And the first question asked is for the type of addition reaction taking place in reaction X. In this question, we're not to tell them it's an addition reaction, because they've told us it's an addition reaction. It's which specific addition reaction. If we look at the difference between our original chemical and our product of reaction X, you should notice that we've got 2 more hydrogens than we had originally. That means we're going to have added hydrogen. That is described as a hydrogenation reaction. So spotting what we're adding and then remembering that's called a hydrogenation for that mark. We're asked which chemical reacts with propene to form chemical Y. If you look at what's happening, we're adding on 2 chlorines. That means we're going to be adding chlorine molecule to this chemical for that. In this question, they're talking about the spray that's used to mark out the position of free kicks in football, and they're asking us about the elements present in a hydrocarbon. That is hydrogen and carbon. Next one, we're now talking about intermolecular forces. We're asked to compare butane to isobutane. It tells us that butane has a higher boiling point, as we can see there. -1 is closer to 0, so it's higher than -12. It has to have stronger intermolecular forces. So stronger and intermolecular forces would be correct for that. That brings us to the end of the topic. Hopefully you are more comfortable at naming and drawing hydrocarbons, talking about intermolecular forces, comparing saturated and unsaturated compounds, and also looking at addition reactions that can happen. Thanks for watching. Goodbye.